Hey again, everybody. Chem 127 once again here, lesson number 12. Um, this is the first of the home stretch of lessons that now comprises the last three lessons in which we sort of bring the pieces of the puzzle together. This one ends up being a bit of a laundry list of maybe some of the less chemical things. We'll talk about We'll actually look at the temperature data over the last few time periods, and start looking. Well, what's happened to climate change? We've talked about all these things that affect it. What's been going on? Talk about the effects of the sun, or changes in solar radiation, which can be the sun or variations in the Earth's orbit. Actually, look at a really classic scientific experiment called the Vostok ice core, which is some of what gives us some insight into these temperature histories, but is a great story in and of itself. And then a little bit about the thing that makes this story not so easy to understand, these things called feedbacks, which is the way that Mother Nature's processes are intertwined, and something happens and it usually affects something else. A bit of that everything is connected story that the ecologists like to talk about. It actually pertains to the transaction of energy between the physical and chemical parts of the atmosphere too. So maybe there's a lesson there about how to think about things, and that lesson is not to think about them in a strictly linear cause and effect way. Some reading here, some things from this EM chapter 14, some things on the front end and on the back end of that big, huge piece that I gave you. And I also want you to start reading these IPCC reports. This is really what we're working on doing here, is for you guys to be able to read these. And notice that I'm saying too, in the original version of this course, this so-called AR4 report from 2007 was the current state of climate change, and that was just updated here in 2013. The good news is there's an update on the science. The bad news is that there's enough complexity in that report that I think it's difficult for the newcomer to understand. And I didn't want to get rid of this because I think the AR4 report really lays out the case for this. So the downside is we get a little bit more work to do. But I think we're going to read this, and then my last lesson, which is a new addition to this course at this point, is going to be going in really pointing at how these, what's different and what's more complex about the science in the AR4. The end result, the main conclusion, is the same thing. So that's where we're going. And then one more homework assignment. What we're doing. But again, the goal here now is to assemble the sort of scientific case that supports this global warming hypothesis, or what I like to call the scientific case for global climate change. And I'm going to want you to be able to articulate that, or re-articulate that in your final essay. So let's go do this. Okay, and I gave you a few handouts today to print out. This is one I'm going to refer to a lot here originally, just because this really shows how climate has varied over the long term and the short term, and how that variation is different. And the idea here is that we've got average global temperature plotted as some function of time, and these graphs are sequential. These are the top two on your sheet, these are the bottom two. And the idea of this gray area is that this gray area, this entire graph would be that little gray area on that graph, and then this little gray area is that entire graph, and then this little gray area is that entire graph. And the main point of these things is to say the climate has by no means been stable over the long term. Average global temperature has varied a lot, especially over long time scales, although it hasn't varied as much over shorter time scales. If we go back the last 100 years or so, we're coming through a long period of climate stability here that by and large corresponds to the rise of the Homo sapiens as the dominant species on this planet. But over the last 100 years or so, there has been two distinct warming periods. One that ranges from, say, 1915 to 1945, where then it either flattened off and leveled out again, and then it's been warming ever since about 1975. There's two distinct warming periods there, and it looks as though they have distinct causes, which is why I'm making a big deal as to point two of those things out, and why I asked you about that on your homework. But the range of temperature variations is about 0.6 of a degree C. And by the way, for every one of these, we're at the top of it. So while I'm quoting a range, it's really like how much colder was it within that last time frame. Okay, moving back to 1,000 or 1,500 years, 1,400 years. That range is 1.5 degrees C. And you can see here now that there was this cold period that lasted just prior to 1,500 and then again into the early 1800s. This data probably overestimates the degree to which this time period was cold, but there's no question that it was colder. Temperatures from this time are a little bit debatable, and they vary quite a bit by region. I mean, as you go further back, the data is going to be less good. Most of this comes from historical record, meaning you found a weather chart in a castle or somewhere in Europe and inferred the temperature from it. This period here is called the Little Ice Age. You'll hear climate change folks talk about that a lot. It wasn't like the big ice ages like we have back here, so keep that in mind, and we'll talk about that a little bit more in terms of a possible cause recently. But at this period of time, things like, they had cold winters in places like England where they normally didn't have cold winters, and the River Thames used to freeze and people would ice skate on it, and started playing a game that ultimately became ice hockey there, and so on and so forth. Now, going back to tens of thousands of years before present, or hundreds of thousands of years, this kiloyears before present, that would be 150,000 years ago, that's 30,000 years ago. The climate has varied a great deal by about 6 degrees Celsius in total. And these cold points here on these graphs are the things that we call ice ages. Now, the basic idea here is that different things affect climate on different timescales. And I think one of the naive perspectives that you see on global climate change is that while climate has varied like mad over hundreds of thousands of years, and we've had ice ages and the such, so what we're seeing now can't be that big of a deal, but we're looking at a different time window. And I also note that, again, we've been riding on the top of one of these ice ages since we've been around, and we are headed upwards from there. So again, I think that dismissive viewpoint is a little naive, and I would discourage you from adopting it at face value. We're going to make a much more refined consideration of what's really going on here. But in all fairness, the climate has been no means stable for the long term. And it has been that way long before we started messing with the climate system. And that part of that is absolutely true. Okay. These longer term variations, so what I'm going to do here is go back and talk about variations, non-chemical variations on these things working back to the present. These cycles of glaciation, these long-term variations in climate, are actually due to changes in solar radiation, but not because the sun is fluctuating, because the Earth's orbit varies a little bit with time through a few different ways. But I think that there's this thing called the eccentricity, which is probably the easiest one of these to see, is that, over the period of about 100,000 years, the Earth's orbit varies to something that's more circular and less elliptical, to something more elliptical. And obviously, these pictures are very much exaggerated. This is a very subtle effect. But as you move away from the sun, those divergent rays become less concentrated on the Earth's surface, and the radiative flux, the solar flux, goes down during times when the sun is further away. Now, why that doesn't average out when the sun is closer, I'm not really sure about that. But I think it's because when it's further away, it's further away, and when it's closer, it's closer. And these rays diverge faster than, so in other words, the amount of radiation that you would lose by getting farther away here is more than the radiation you would gain by being closer there, and it's a subtle mathematical thing. I did locate a couple of YouTubes to isolate these other motions in the Earth's orbit that are called the Milankovitch cycles. I just want to kind of preview one of these things here. And they're on the D2L page, but this one's kind of silly because you got these physicists trying to act this out in real time, but it goes through each one of these with one of these dorky guys kind of swirling around a labyrinth somewhere. It looks kind of like near Phoenix Park or something like that, but obviously it's not. So here's this other motion called the precession, which has to do with the Earth, sort of its axis sort of wobbling in a circle as it goes around. And now this guy's going to wobble around in a circle. And notice that the sun is, so this guy's the sun, and then here's his friend who's going to precess and wobble back and forth. And I'll just let you guys watch this on your own. That's just a way of sort of illustrating what's going on. I'll show you some pictures here on the next slide that make a little more sense of this, I hope. But before I do that, I just want to make sure that we understand seasons, because if we understand how the seasons work and how a change in the sun's angular orientation affects the amount of radiation that reaches the surface, then you'll be able to maybe buy into this idea of these Milankovitch cycles a little bit better. But the idea is the Earth is tilted on its axis, so when it moves around the sun, when it's over here, I don't know whether you can see this or not, or when it's, let's do this here. Over here, when it's tilted this way, the southern hemisphere is getting more direct sunlight. It's not that it's closer, it's that it's getting more direct sunlight. And when it's over here, the northern hemisphere is getting more direct sunlight. And it's just like, so if you guys are looking through this, and you're the sun, and this is a piece of ground, okay, that radiation is hitting perfectly directly on the ground in a perpendicular manner, and if the sun is tilted in the sky like this, the shadows get longer, and at the same time that radiation that was here is now spread over a much larger area. So it has to do with like tilting the angle of the sunlight and spreading the same amount of area over same amount of radiation over a larger area, which is why this quantity flux is important. We're not changing the flux because the sun is getting brighter or not. We're changing the area that that energy per unit time is striking, and as the same amount of energy hits a larger area, the flux is going to go down. And again, flux is energy per unit area. So that's kind of how seasons work. But the idea is that the Earth not only gets more eccentric or less eccentric as it goes around the sun, it kind of spins and wobbles on its axis, and there's different names for these. So the elliptical part, again, is the eccentricity. The tilt varies a little bit, you know, on a time scale of 41,000 years. So the Tropic of Cancer, as we know it, the 23.5 degree thing, moves a little bit over the course of 41,000 years, which is a long time, obviously. And then there's also this kind of wobbling thing like that dorky dude was doing in the last video, which has to do with these things. So these things are, and that's sort of like when it notice there's a top here. You'll notice that as the top is about to die, it sort of starts doing this, and that's precession. I don't claim to understand this a lot, other than to just maybe trust the people who believe in these so-called Milankovitch cycles, and I think that this is a pretty well-established theory at this point. But the idea here is that you can take all of these cycles and their effect on the solar flux, and then you can see that the solar flux sort of modulates a little bit and corresponds to the cycles of glaciation, hot and cold. So, you know, therefore, I don't think this is the most convincing thing. But anyhow, the long-term things are thought to be due to variations in the Earth's orbit, and that's what I want you to take from this. Okay, so summary. Okay, these things, temperature history over tens or hundreds of thousands of years, cycles of glaciation, okay, 6 degrees Celsius, and these are due to variations in the Earth's orbit. And just to put this in perspective here, if you go back to this cycle of glaciation right here, at this point in time, you know, it's a lot more significant than it was now, but if you go back 6 degrees Celsius, Eau Claire was underneath a mile or two of ice at this point in time, and even back here at this 20,000 year ago cycle of glaciation, the polar ice cap had extended all the way to the edge of Bloomer, where the so-called Ice Age Trail is in this area, and there's some really interesting geological features up there. It's a great place to hike. So while you might say, oh, what's 0.6 of a degree isn't this big of a deal compared to 6. 6 means a radically different place, okay? Sort of beyond our comprehension. So there, I'm going to pause there and move on to the next part.